Hi everyone. In one of the last videos we talked about the idea of dispersion, which is the idea of how spread out the data values are from each other in a data set. I wanted to start by giving you another example of some data sets with different amounts of dispersion. Let's imagine that I'm teaching a class of 4 students, and all 4 of my students are taking an exam, and the mean of my class is 75. In other words, if I added the 4 exam scores and divided the total by 4, the mean would come out to 75. So here's one possibility. It could be that all 4 of my students got the same exam score, and I'll show you what that looks like. I'm just going to make a diagram. If all 4 of my students got the same exam score, if they all got 75, then the mean of the class would be 75, and the data would have no dispersion to it because every value is the same. But here's another possibility. Maybe 2 students got a 74 down here, and 2 students got a 76 up here. So in this example, I was saying that all 4 students got a 75 and the mean was 75. In this example, I'm saying that 2 students got 74s and 2 students got 76s. And the mean of this class would also be a 75 because if you added these 4 numbers and divided the total by 4, you would get 75. And you can also see that 75 is the center point of the data, because we talked about how the mean is usually somewhere near the center of the data. These 2 data sets both have a mean of 75, but the difference between them is that this data set has more dispersion and this data set has less dispersion, because these values are more spread out further away from the mean, and these data values are all closer to the mean. And I said this is low dispersion, but it's actually no dispersion at all. This is higher dispersion. And one way to think about dispersion is based on how far the data values are from the mean. When the data values are more spread out and there's higher dispersion in the data values are further away from the mean at the center. So here we can see that when all 4 values were 75, each value was exactly at the mean. So the distance from each value to the mean is 0. This person's exam score is 0 away from the mean. This person's exam score is 0 away from the mean. This person is 0 away from the mean. And this person is also 0 away from the mean. So we could say that the distance from each value to the mean is 0 in this data set. In this data set, each person is 1 away from the mean, because this person who got a 74 is 1 away from the mean. This person who got a 74 is also 1 away from the mean. This person who got a 76 is 1 away from the mean. And this person who got a 76 is also 1 away from the mean. So the distance to the mean in this data set is 1, because every value is 1 away from the mean. So in the data set with lower dispersion, each value was 0 away from the mean. because they were all equal to the mean. And in this data set with higher dispersion, each value is now 1 away from the mean. So the values are getting spread out further away from the mean in both directions. So now each value is further away from the mean than it used to be over here. So we can make some bars to show these distances. And if the value is 1 below the mean, we'll mark the distance as a -1 to show that it's 1 below the mean. So this would be a -1. Well, actually we'll leave off the signs, because if we leave off the signs, then they become absolute deviations. So each of these is a 1. All this 1 right here is saying that this value is 1 away from the mean of 75. This person got a 74, and they're 1 away from the mean. This 1 right here is saying that this person who got a 74 is 1 away from the mean. This 1 right here is saying that this person who got a 76 is 1 away from the mean. And this 1 right here is saying that this fourth person who got a score of 76 is also 1 away from the mean. So all 4 people are 1 away from the mean. Each person in the class has an exam score and an absolute deviation that shows how far the person is from the mean. So each person's absolute deviation is 1. Now, what if I taught the class, and what if I was teaching a class of 4 students, and I gave out the exam to the 4 students, and this ended up being the outcome? 2 students get a 73. And 2 students end up getting a 77. Now the data has more dispersion to it than it did here, because now each person's exam score is 2 away from the mean. And once again, we can make these bars to show how far each person's score is from the mean. So now this first person who got a score of 73 is 2 away from the mean. So I'll put a 2 there. This person who got a 73 is 2 away from the mean. This person who got a 77 is 2 away from the mean. And this person who got a score of 77 is 2 away from the mean also. So each of my 4 students has an exam score that's 2 away from the mean. So now the distance to the mean is 2. So the point that I'm making right here is that when the values get more spread out from each other, the distance to the mean increases. So as the dispersion of the data goes up, the distance to the mean goes up along with it. This data set had the least dispersion, and the distance to the mean was 0. This data set had higher dispersion, and the values were further away from the mean. They were 1 away from the mean. This data set has even more dispersion than this data set, and the distance to the mean has gone up because now each data value is now 2 away from the mean. So as the dispersion of the data goes up, and the distance to the mean goes up along with it, because when there's more dispersion, the values are moving further away from the mean in both directions. So this has the highest dispersion. So now let's think about if I wanted to describe the dispersion of my students' exam scores to someone, could I just tell them the distance to the mean? For example, could I just tell someone that my students were 1 away from average, or my students were 2 away from average? Well, it would be nice if it was that simple, but the problem is, in a real classroom, not every student is going to be the same distance from the average. I mean, not every student will be the same distance from the mean. Some students might be 1 away from the mean, other students might be 5 away from the mean, and other students might be 10 away from the mean. So I can't just say that every student was 1 away from the mean, or every student was 2 away from the mean. I'll show you an example of what I mean by what I'm saying right now. What if instead of getting these exam scores, I got these exam scores? Where students' exam scores were 73, 74, 76, and 77. Well, this student who got a 74 is 1 away from the mean. This student who got a 76 is 1 away from the mean. But this person who got a 73 is actually 2 away from the mean, because they're 2 below the mean. And this person who got a 77 is 2 away from the mean also, because this person has a score that's 2 above the mean. So this person who got a 73 is 2 away from the mean. This person who got a 77 is 2 away from the mean. And what if I had an outcome like this, where one student was out here, and one student was out here? So now the exam scores are 72, 73, 77, and 78. Well, this score of 73 is 2 away from the mean. This score of 77 is 2 away from the mean. But these 2 other exam scores are 3 away from the mean, because this person who got a 72 is 3 below the mean of 75. And this person who got a 78 is also 3 away from the mean of 75. So if I got this outcome or this outcome, I wouldn't be able to just say that each of my students is 1 away from the mean, or each student is 2 away from the mean, because each student has his or her own distance from the mean. I mean, the distances aren't all the same. What I could do in this situation is calculate the average distance to the mean. So what I could do is add up these 4 distances and divide the total by 4. So I have the average distance from each value to the mean. If I added these 4 distances up here, they would add up to 6, and 6 divided by 4 equals 1.5. So now I can say that the average distance to the mean is 1.5. And what if I added up these 4 distances and divided by 4 to get the average distance to the mean of this data set? Well, the 4 distances would add up to 6, 10. 10 divided by 4 is 2.5. So what I could tell someone is that in my class, the average distance to the mean was 1.5. And that person will be able to picture the amount of dispersion in my class. They'll know that the dispersion looks like this. And if I tell someone the average distance to the mean was 2.5, the person will know that the data looked like this. So when the average distance to the mean comes out to a lower number, like it does here, it means that there's less dispersion, like this outcome right here. And if the average distance to the mean comes out to a higher number, it means that there's more dispersion, like we see over here. And over here, well, if all 4 distances are 0, then the average distance to the mean would just be 0, because we'd be adding 4 zeros and dividing by 4. So there isn't really a point in us calculating the average distance to the mean of this data set, but let's do it anyway, just to show how it comes out to 0. There's actually a name for this value that I've just calculated. The average distance to the mean is called the mean absolute deviation, or the MAD, because each distance to the mean is called an absolute deviation. So this is an absolute deviation of 1. This is an absolute deviation of 2. This is an absolute deviation of 1 again. And this is an absolute deviation of 2. So each person in my class has both an exam score and an absolute deviation that shows how far the person is from the mean. And when you're calculating the MAD, you calculate the mean of everyone's exam scores. I'm sorry, I didn't say that right. To get the MAD, you calculate the mean of everyone's absolute deviations. So each person has his or her own absolute deviation, and the MAD is just the mean of all of those absolute deviations. So this class has a MAD of 0. This class has a MAD of 1.5. and this class has a MAD of 2.5. So as the data gets more spread out, the MAD goes up, because as the data gets more spread out, the values move further away from the mean, and the absolute deviations get bigger. And since the absolute deviations are getting bigger, the mean of the absolute deviations is getting bigger. So here, all 4 absolute deviations are 0, which means that the MAD is 0. Here, half of the absolute deviations are 1s, and the other half of them are 2s. So if the absolute deviations are 1, 1, 2, 2, the mean of those absolute deviations is 1.5. When we go here, instead of being 1s and 2s like they are here, the absolute deviations are now 2s and 3s. They're now 2, 2, 3, 3. So the absolute deviations have gone up over here. And since they've gone up, the MAD has gone up. It's gone up from 1.5 to 2.5, because these absolute deviations have a higher average than these absolute deviations do. Remember that the MAD is just the average of all of the absolute deviations. So as the dispersion goes up, the absolute deviations get bigger, and therefore the average of the absolute deviations gets bigger. That's why the MAD goes up when the dispersion goes up. And the way I've calculated it here doesn't look the same as the way I calculated it in my PowerPoints, because I wanted you to look at the concept a little bit differently and just understand it visually instead of with lots of columns like I did before. But I'll actually add in those columns right now, just so you can connect it. You can connect what you're seeing now to what you saw in the PowerPoints. So when you calculate the MAD, you have a column of data, which in this case are the exam scores of the 4 students. In this class, all 4 students had an exam score of 75, so that's my data. The mean of the class is 75. If you added these 4 numbers and divided the total by 4, you would get 75. If you want to double check, you could add these 4 data values and divide by 4, and you would get 75. So remember, you have to subtract each value by the mean. When you subtract each data value by the mean, the answers are called deviations. To get the MAD, you have to go one step further and create a column of absolute deviations. So, well, if the deviations are all 0, then the absolute deviations are also 0, because the absolute value, the absolute value of 0 is 0. So I'm just going to copy the column over again. And then, well, every number in this column is just the absolute value of each number in this column. So 0 is the absolute value of 0, 0 is the absolute value of 0, and again 0 is the absolute value of 0. I'm going to add the 4 absolute deviations and divide by 4, because remember I have to divide by the number of absolute deviations. There's 1, 2, 3, 4 of them. So I divide by 4 so that I can get the average or the mean of all of the absolute deviations in here. And it comes out to 0. So like I said, the MAD comes out to 0 if all the values are the same and there's no dispersion. Now let's do the same thing over here. Now my data values aren't all 75 anymore. One student got a 73. And one student got a 77. So my values are actually 70, 73, 74, 76, 77. And if I subtract each value by the mean, I get a deviation. This one is -2. This one is a -1. This one is a +1. And this one comes out to a +2. 77 minus 75 is 2. Now these numbers that I showed up here aren't actually the deviations. They're the absolute deviations, which we're going to calculate in a second. The absolute deviations are all positive, but the deviations can be negative or positive. So I'll actually label the deviations up here. This person's exam score of 74 has a deviation of -1 because they're 1 below the mean. -1 means 1 below the mean. So this person who got a 74 had this deviation of -1 right here because they're 1 below the mean. This person who got an exam score of 76 is 1 above the mean. So their exam score is 1 above the mean of 75. So their deviation would be a +1. That's where this +1 comes from. So the exam score of 74 is 1 below the mean of 75. So this person who got an exam score of 74 has a deviation of -1. I labeled it up here. This person who had an exam score of 76 had a deviation of +1 because that person is 1 above the mean. So all a deviation shows is how far a person is below the mean or how far a person is above the mean. -1, if a person has a deviation of -1, they're 1 below the mean. If a person has a deviation of +1, they're 1 above the mean. This person who got an exam score of 73 is 2 below the mean of 75, which means that their deviation would be -2. That's where this -2 comes from. This person is 2 below the mean of 75. This person who got an exam score of 75 is 2 above the mean. So their deviation is +2. So every person has a deviation, and an absolute deviation. These four numbers that I'm circling are the regular deviations. These four regular deviations show how far each person is from the mean, but if the person is below the mean, it's a negative number, and if the person is above the mean, it's a positive number. So 1 below is -1, 1 above is +1, 2 below is -2, and 2 above is +2. The absolute deviations also show the distance from each value to the mean, but the difference is that the absolute deviations are always positive. Remember, these are the absolute deviations, which just mean all they show is that this person is 1 from the mean, this person is 1 from the mean, or 2 from the mean and 2 from the mean. So if we, in order to get the absolute deviations down here, we would have to just take off the negative signs from the deviations and just change -2 to 2, -1 to 1, and these two stay the same. These four absolute deviations are just these four numbers that I've had up here all along. We calculate the mean of them by adding them and then dividing the total by 4, because there's 4 numbers in the column. 1, 2, 3, 4. And the answer comes out to 1.5. Like it did here. So it's the MAD, but it's really just the average of all of the distances to the mean. It's the average of all 4 of these distances. If we want to get the MAD over here, we do the same thing again. So I'm going to go through all of these steps again, but once we get to the absolute deviations, we're going to see that the absolute deviations come out to 2, 2, 3, 3, because the absolute deviations are really just the distance from the value to the mean. So now the values in this data set are 72, the first one is 72, 73, 77, and 78 up here. Now let's think about what these deviations are going to come out to. This person who got an exam score of 72, which is this person right here, is 3 below the mean. If they're 3 below the mean, their deviation should be -3. And let's see if that's true. 72 minus 75 is -3. So this person does have a deviation of -3. This person who got an exam score of 73 is 2 below the mean of 75. So this person's deviation should be -2. Well, 73 minus 75 is -2. This person right here, who got an exam score of 77, is 2 above the mean. So if they're 2 above the mean, their deviation should be +2. And 77 minus 75 is +2. So that person does have a deviation of +2. This person who got the exam score of 78 is 3 above the mean of 75. So this person's deviation should be +3. Because if they're 3 above the mean, their deviation is a +3. 78 minus 75 is +3. Now, in order to change these deviations to absolute deviations like they are here, we have to take off the negative signs. Because what we have right here right here we have the values that are deviations that actually show whether a person is below or above the mean. Because remember, this person is 2 below, it's -2. 2 above is +2. 3 below is -3. 3 above is +3. So these two values have negative signs. These two don't have negative signs. In order to make them absolute deviations like they are here, you have to take off those negative signs. This becomes 3. This becomes 2. These two stay the same. And now we have our absolute deviations that we had up here all along. They add up to 10. 10 divided by 4 is 2.5. So the MAD, or the average distance to the mean, is 2.5. So on average, a student in this class is 2.5 from the mean in either direction. Now the MAD is a pretty simple and straightforward way of measuring the spread of the data, but actually the MAD isn't commonly used as a measure of dispersion, and in a few minutes I'll get into the reason why it's not used. But first I want to show you the value that actually is commonly used, which is called the standard deviation. And the standard deviation is a value that actually comes out close to the MAD. It doesn't come out exactly the same as the MAD, but it usually comes out to a value that's close to the MAD. And I'll show you how it's calculated. What you have to do is you have to create a new column, which is a column of squared deviations. If you want to get a standard deviation, the first step is to get these squared deviations. To get the squared deviations, you have to multiply each deviation by itself. So for example, here it will be -2 times -2, -1 times -1, 1 times 1, and 2 times 2. But it turns out that actually you can get the same answers. Well, oh no, I won't get into that. We'll just do it the way we've been doing it. So 0 times, you have to multiply each deviation by itself. 0 times 0 is 0. 0 times 0 is again 0. So all of these squared deviations will come out to 0. What you have to do next is calculate the mean of the squared deviations by adding them like we did for the MAD and dividing the total by the number of squared deviations. There's 1, 2, 3, 4 of them, and it comes out to 0. Now, this number that I've just calculated, which is the mean of the squared deviations, isn't actually the standard deviation. It's another number called the variance. You have to go one step further to get the standard deviation. So this was the mean of the absolute deviations was the MAD, and the mean of the squared deviations is called the variance. The standard deviation is the square root of the variance. So you have to take this variance right here and put it under a square root sign. And the answer is the standard deviation. In this case, the MAD and the variance, in this case, the MAD and the standard deviation are exactly the same. But they don't always come out exactly the same. They're usually just close. Now let's do the same thing over here. -2 times -2. Once again, we have to multiply each deviation by itself, which, in other words, we have to square each deviation. Squaring just means multiplying a number by itself. So -2 squared is -2 times -2. That -2 times -2 comes out to 4. -1 times -1 is 1. Whenever you multiply a negative number by a negative number, you get a positive answer, because the negatives cancel out. 1 times 1 is 1, and 2 times 2 is 4. So -2 times -2 and 2 times 2 come out to the same answer, because whenever you multiply a negative number by another negative number, the negatives cancel out and they disappear, and you get a positive answer. So here, all we're really doing is 2 times 2, and it comes out to 4. So these come out to the same answer. And just the same way, if you multiply -1 times -1, you're really just doing 1 times 1, because the negatives cancel out. So here, I'm squaring -2. Remember I said squaring is multiplying a number by itself. So here I'm squaring -2. Here I'm squaring 2. I'm squaring -1, and I'm squaring 1. And that's how I got these these 4 answers here. So here, all I did is I squared all 4 deviations, and I got these 4 answers. Now the variance, remember I said the variance is the mean of the squared deviations? To get the variance, you have to add the squared deviations and divide by the number of squared deviations. They add up to 10, and there's 1, 2, 3, 4 of them. 10 divided by 4 is it's 2.5. So here we have our MAD, which was the mean of the absolute deviations. Here we have our variance, which is the mean of the squared deviations. The standard deviation is the square root of the variance. So you have to take the variance and put it under a square root sign. And this will come out to 1.58. So it does come out, this standard deviation does come out close to the MAD. So we have the MAD is 1.5, the variance is 2.5, the standard deviation is 1.58. Now I did get into the adjustment that I talked about last time, which is, I said if the data is from a sample, you divide by, instead of dividing by 4, you would divide by 3. You divide by 1 less. And I just didn't get into that in this video because I'm saving it for a few minutes later. So I just did it without that adjustment. So here's the MAD, the variance, the standard deviation. And the squared deviations over here would be, well, -3 times -3 is 9. -2 times -2 is 4. 2 times 2 is 4. And 3 times 3 is 9. Notice how we talked about how the absolute deviations went up when the spread goes up, because in this data set, our absolute deviations were 2s and 1s, and in this data set, they were 2s and 3s, because the numbers are further away from the mean. Notice how we can see also that when the spread goes up from this data set to this data set, the squared deviations also go up. Here there are 4s and 1s in this data set, but over here, in this data set, there are 9s and 4s. So the squared deviations have gone up from 4s and 1s with this data set to 9s and 4s with this data set. The variance and standard deviation are calculated based on the squared deviations. So if the squared deviations are going up, the variance and standard deviation will go up along with them and come out to higher numbers. So basically, as the absolute deviations go up, like they do here, when the spread goes up, the absolute deviations go up, and that causes the MAD to go up. When the spread of the data goes up, like it does here, the squared deviations also get bigger, and that causes the that causes the variance and standard deviation to go up. And what I can actually show you that that's true. If to get the variance, we need to add all of these and divide by 4. So 18, 26 divided by 4. Sorry, I'm a little bit out of room, but I'm just dividing the total of the squared deviations by the number of squared deviations to get the variance. .5. So 26 divided by 4 is 6.5. That's the variance of this data set. With this data set, when I added the squared deviations and divided by 4, my variance came out to 2.5. But now in this data set, when I added the 4 squared deviations and divided by 4, I got a variance of 6.5. So the variance did go up. And it went up just because the squared deviations are bigger. Instead of being 4s and 1s, the squared deviations are now 9s and 4s. So here I actually have some more room here. So 6.5. The MAD was 2.5. The variance is 6.5. And let's get the square root of 6.5 to get the standard deviation. About 2.5. Or actually 2.55. So the standard deviation came out to about the same as the MAD, like I said it would. They usually come out to about the same. So the point that I'm making is that all three values go up when the spread goes up. When you go from this data set to this data set, you're going the MAD, variance, and standard deviation are going up. All three of them are going up because here with this data set they were 1.5, 2.5, and 1.58. But over here they went up to 2.5, 6.5, and 2.55. So each of these three values became larger over here. So when the spread goes up, like it does from here to here, all three values, all three measures of dispersion will increase. And I said that the standard deviation is most commonly used to measure dispersion. And the standard deviation is a number that comes out close to the MAD. So remember that the MAD is literally the average distance to the mean. The standard deviation is a number that just, well, you could say that it's roughly the average distance to the mean because it comes out roughly the same as the MAD. So the MAD and standard deviation are almost the same thing, but they have just different formulas. And the variance is, well, it does have some uses in more advanced topics, but for right now you can just think of the variance as just a step along the way to get the standard deviation, because you have to get the variance first and then get the standard deviation afterward. So just think of it as being a step along the way to get the standard deviation, because you get the mean of the squared deviations, that's the variance. You go one step further with a square root, you get the square root of the variance, that becomes the standard deviation. Now let's think about why the standard deviation is more commonly used. Well, in today's topic, we'll talk about how if a group of people follow a normal distribution, then it's actually possible to predict how many. Well, I'll show you. It's actually possible to predict how many people will fall between one standard deviation below the mean and one standard deviation above the mean. So imagine this is one standard deviation below the mean, and this right here is one standard deviation above the mean. If a population has a normal distribution, then it turns out that 68% of people will fall between one standard deviation below and one standard deviation above the mean. For example, we know that IQ scores in the general population have a mean of 100, and the standard deviation of people's IQs in the general population is 15. So if I was able to record the IQ scores of the entire population of the entire world, and I calculated the mean and the standard deviation of all of those IQ scores, I would get 100 as the mean and a standard deviation of 15. The IQ test has actually been designed so that the mean will be 100 and the standard deviation will be 15. So that's actually on purpose. So 15 below 100 is 85. 85 is one standard deviation below the mean. If you go one standard deviation above the mean, it's an IQ of 115. It's 15 above. It turns out that 68% of the general population has IQs between 85 and 115, because that's one standard deviation below and 1 standard deviation above the mean. And the reason why, one major reason why the standard deviation is commonly used is because it is possible to predict what percent of the population falls between 1 standard deviation below and 1 standard deviation above the mean. But it's not possible to predict what percent of the population falls between 1 mad below and 1 mad above the mean. That's not predictable. So the mad isn't useful in the mad isn't useful in this situation, but the standard deviation is. So if someone asked me what percentage of the population has IQ scores between 1 mad below 100 and 1 mad above 100, there'd be no way for me to know because that's not predictable. But if someone asked me what percent of the population has IQs between 1 standard deviation below the mean and 1 standard deviation above the mean, I can say 68%. So the standard deviation is useful in a way that the mad isn't useful. And one last thing I wanted to get into is that the standard deviation is actually adjusted when the data comes from a sample. And I'll have to get into why you do that. Because let's say right here that we have, well, before I tell you why it's done, I'll just show you an example of, I'll show you one more example of the calculations, and then I'll talk about why we do it. And I'm going to pause this video while I calculate the deviations and squared deviations, and then I'll start the video again.